Okay, so now let's talk about the control of speed and then position. Okay. First, remember, your closed loop, simple, single input, single output control. It means that we've got some reference input, R, to form an error here. This is a plus, this is a minus, and what we're gonna do here is feedback a signal that represents a measurement of whatever variable you're trying to control, right? And that in the model of this guy, we would have a transfer function of our plant, right? In this case, that plant, it could be, for example, the motor for speed control. So we'd have, this G sub P could be the transfer function, right, of that plant. We're going to feed that guy back by making a measurement of it. We might have a transfer function that represents the measurement of this could be a measurement transfer function that takes, let's say this is a variable y. It takes y and it gives us, say a measurement of y, and feeds that back so we can form the error, right? And then in a typical controller, that error would, right, go into some kind of a controller or controller transfer function to give us the driving input. And commonly, we'll also say that there could be disturbances that come into the plant. So we would add what comes out of the controller with some other input U that comes from disturbances, and that would give us our total U. And so, the Y over the U is the GP plant transfer function, right? And I'm not going to go through all that. I assume in your class you've covered that, but just a simple formula to give us the closed loop transfer function of the feedback controlled system. You have, we want to solve for Y. This is equal to two pieces. The first part is due to the, and I'm just going to write this out. Okay, so you have the formulas. Part due to disturbances, right? And part due to the reference input, right? And note that, and this is the reference input, right? So this is due to this. So Y changes due to disturbance effect, which in our case, we're not going to deal with that. And this is due to right command inputs. And that's what we're looking at. So R has to have the same units as Y, right? If we're doing speed control, then the reference input is going to be a desired speed, right? And the output is going to be the motor speed and so on. So this little formula, again, you plug in what you know for your transfer functions, and you can get a transfer function, we call the closed loop transfer function, say between, so for example, to get the response Y to the reference input, you just need GC GP over 1 plus GC GP times H, right? And that's your transfer function. This guy right there, right? That's your characteristic equation. And remember how you can look at the roots of the characteristic equation to tell you how you want to design the system, whether the system is stable, and so on. So what we're going to be looking at in a second is how we can, because when we put a controller in here, you see the controller now allows you to change the characteristic equation. The essence of simple control design like this is to choose the GC and the H in a proper way so you get the kind of dynamics that you want. They also influence the numerator as well. So you're looking to get the desired response Y for given commands R. Okay. So let's look specifically at the speed control. In that case, what is that going to look like? We're going to take our little Quanser plant, right? And we're going to have, I'm going to have the omega m over Vn. And it's going to give us an output of the motor. Remember, we can measure that guy in different ways. And remember that the Quanser plant makes it really easy for you because they give you a measurement, right, of that guy. So here, I'm going to put the block here. And there's different ways that you can measure this. This sensor is either a TAC or an encoder. But remember, the encoder gives you position, so it actually requires you to take a derivative of that. So the TAC gives you a direct, right, direct omega measurement. So it's going to give us a measure of omega that we can feed back. See, I hate that I didn't put my lines on the lines. That's going to be in the middle of it now. Yeah, it's an obsessive thing, but there you go. So here's our sort of estimated measure of the speed of omega. Here's our desired motor speed, our commands. And then we form an error that goes into some transfer function here for our controller. And then we're going to just assume there's no disturbance. And the output here, right, is in a sense the input voltage. There's a lot embedded in here. Like, you know, realistically, what's happening is that controller also has the voltage is coming from that H bridge and all that. But think of this as just this ideal model here. Okay. So you can get a nice little transfer function for that. You can derive, right, the closed loop transfer function. And I think I have, yeah, the first, like what would we want to, oh, also the controller here. If we just want, if we just use, I'm gonna change my notation so that it matches what is on the Quanser BIs that you're gonna use. Little kp here is equal to the proportional gain. So if we just have GC equal to a constant gain, so this gives us a proportional controller, because what we're gonna see is that the error, right, is now desired minus the measured, and then the command, you know, U, which is a voltage in, is simply just Kp, you know, times that error in speed, right? And it's just a, you know, proportional gain. Okay. You could, so if GC equals Kp, and you know, you know what GP is, because that's omega m, we derive that, and you know what it's K over tau S plus 1. You know the K, you know the tau, you know the Kp. We're going to assume that we have a perfect measurement, H equals 1. There could be some error in there, but perfect measurement just means that it's a 1-to-1. Then look, you can derive the closed loop transfer function, which is going to be the omega, the motor, over, note, it's the command, that's the input now, and you can derive this guy. Excuse me. So, yeah, I'm hitting in my sort of my outline. The pre-lab problem number 1, I'm asking you to describe the derivation of the motor model. I've done that for you, so you should be able to do that. Present it in the form of an open loop transfer function, right, between motor shaft speed and input voltage in symbolic form, which means in parameters, right? So plug in any numbers. And then using the motor parameters that you have, calculate values of K, and I should have put this before in that line, and tau. So you should have numbers for k, a number for tau, right? And that's pre-lab question number 1. I should have given you that one first. I think that should be, hopefully based on what we've talked about, pretty straightforward to do that first pre-lab. And now the derivation of the closed loop transfer function, just plug everything in there. Omega over omega d, right, is just GC GP over 1 plus GC GP times H, right? So when you do all that, you have a little Kp, that's Kc, and you have K over tau S plus 1 over 1 plus, and this is the same thing down here, right? And then you have times 1 here because we're assuming that we have a nice ideal measurement. When you work all of that through, collect terms and so on, you can show that it's something like Kp over K over 1 plus Kp, little k times big K over, and this is the original tau divided by 1 plus little kp times big K times S plus 1, okay? So look at this term up here, that's just the constant. This term right here, so I like to call that like a new tau, which is like the closed loop tau. And you can call this like a big K closed loop K. So it's the same form, right? Adding a proportional control, you know, same as the open loop transfer function, you know, but different K and tau. The tau changes. In fact, you should find that the tau is smaller, the system can react faster, and so on. And it also, you know, you've changed this from an open loop system to now an error feedback control system where now you can specify an omega, right? The desired omega, and it'll try to achieve that through that omega m. And if you look at the steady state value here, you can see, I might be jumping. Okay, look, pre-lab question number 2, sorry. Show the derivation of the closed loop transfer function. I just did that for you. Again, don't plug in numbers. Just want you to show that to the TA. Again, recalculate the K and the tau, show that they're different. Easy. You're almost done with the pre-lab. So one of the things I'm going to ask you to do then is to build this little controller, right, in the lab, and it makes it really easy because let me. If anything comes up, any question, just let me know, and I'll keep an eye on the chat, but it doesn't look like any of you have any questions so far. There it is. So this is the little template that we're gonna ask you to use in the first step in the lab. And you know, they give you this nice little setup so you can open it up and now you can build a little feedback controller. Remember this guy right there, oops. This, I'm supposed to be able, there you go. This guy gives you one of the outputs here, right? You know, you can go to attack, oops. And so you can easily now wrap that around. I'm gonna erase that if you don't mind. So I can just draw. You're gonna want to move this guy over, but let me show you what you, I would move, when you get into lab, I would move this guy farther over here. So I'm gonna draw him over here, right? It's gonna be messy, but kill this guy. So here's, and now take your little, this is your omega measurement, right? And come back over here, form a little, so here's gonna be the omega that you want. This is the omega that you measured. There's your error, right? Multiply it by a little gain, put a KP in there. and then this is your drive voltage right in there. So simple. And then this guy right here can go to a little plot. Show your output. Okay. So you're going to build that guy in the lab. Nice. And I'm going to ask you to say, hey, what's, you know, I want to control omega to some desired level of error, right? So in other words, you'd like for omega m, omega d at the end, like let's say you gave it a step input in sorry, not in voltage, but in desired, and then you want your motors. It's the first order system, so what do you expect to see when you hit this guy? It's going to jump up, and it's going to do, it's first order, so it's just going to do that, right? And this is going to have the tau of the closed loop system, and so on, right? And then there's going to be some error here. You know, it's not going to be perfect. So you can say, you know, that if you think about it, you know, that should be something like between a ratio that's, you know, some low to some high, you know, depending on what the error is. So you can now take your closed loop transfer function and use that and say, hey, so let's remember, that's going to look like this. Sorry, all the jumping around. If that's going to look something like this, the model, some k CL over some tau CL S plus 1. Remember, in here, you have a KP value. So the question in a real simple design is choose KP so the steady state error, you know, is within let's say 5%, right? So then you can solve for KP. That is, and so what you can do is you can use what's called the final value theorem, right? Let me just, so the final value theorem, you can take that transfer function, right? Remember the final value theorem says if I have some function f of t, if I take the limit as time goes to 0, I can find that value if I know the value in the S domain, like in the Laplace transform, multiplying that by S and taking the limit as S goes to 0, right? So if I know that, now my f of S, what is my f of S in my case? Well, that's my omega m, giving it a step input. So I take my omega m over omega d transfer function, which is k CL over tau CL S plus 1, right? And then I want to find omega m, given that I give this guy a step, right? So omega m is KCL over tau CL S plus 1 times the omega d0 is some value divided by S. This is a step of omega d0, right? So I put this guy in here as my f of S, and then I take the limit as S goes to 0 of S times my omega m, which is this guy. Now, what do I get? Well, you can see I'm going to get basically KCL, right? And remember that KCL is given up above. Let me just go up there so you can see it again. There it is, yeah. It's equal to KP. Is it KP times K? A dog it, I forgot, sorry. Yeah. 1 plus KP over K. Right? You want this guy to be, say, 0.95, right? So you can then solve for KP. Okay, that is, pre-lab number 3. Okay, using the parameters you found from the cube, you're going to know these values, and you can actually get a real KP value. And then it would be neat for you to now go to the lab and say, hey, how well does that work? You know, don't expect it to match perfectly, but you're going to get pretty close, right? It's like you're going to have an actual magnitude for KP. Remember, that was kind of hard to do for the analog meter control because we weren't really sure about the model. It's got all the delay and so on. So, but the test here for the speed control is to see how close you can get.